In this video, we are going to do a simple example of a proof via the contrapositive of a logical statement. So let's just review before we get started, because the structure for a proof by contrapositive and the structure for a direct proof are extremely similar. So what was our structure that we like to follow for a basic direct proof? We needed our proof to have the following parts. So the first thing we needed was to state our assumptions. We always needed to have a to show statement. What is it that we're really trying to prove? We then had a spot where we would introduce all necessary definitions, theorems, variables that we would be using. We then had to do the tricky part of justifying all of our steps, working from what our assumptions are to where we want to be. And then we end the proof. The last thing we do is by establishing what our to show statement was, which is part of the reason it's so important. Now, a proof by contrapositive is going to follow exactly the same formatting, but what we're going to do is we're going to add an extra step to this right at the beginning. And what that is a statement right at the very beginning, before we state assumptions, before we have our to show statement, to say to our reader, as a kindness to the reader, that we're not going to do precisely what they asked. So our reader said, prove if P then Q. And we don't want to just jump right into the proof and say, assume not Q. That seems a little bit illogical. It seems like we're not following what they want us to do. So we're going to alert the reader that we're not going to prove exactly what's written, but instead we're going to prove something logically equivalent, which is this contrapositive statement. So after saying that we will proceed by contrapositive, then it's a kindness to our reader to state what the contrapositive is. And that's necessary for us as writers as well, because we're going to need to know what our new assumptions are. After we insert this initial line into the very front of our direct proof format, then we'll be all set to go. Now, here's the lemma that I want to do an example with for a proof by contrapositive. So it's very similar to something we proved when we did our direct proof statement. In our direct proof video, we proved that if n was an odd integer, then n squared was also an odd integer. Now I would like to prove something similar to that. I'd like to prove the converse. I'd like to prove that if n squared is an odd integer, assuming that n is a natural number, then n is also an odd integer. Now, if you think about this for a little bit, here I'm just saying prove this by contrapositive, and I don't give you any insight as to why you might want to prove something by contrapositive. Part of the reason is if I start dealing with my assumption here, this assumption that n squared is odd, one thing I would do if I were trying to prove this directly without the contrapositive is write n squared as 2k plus 1. And somehow, from that information, n squared is 2k plus 1, I'd like to work my way to n. But the most direct route from n squared to n is by taking a square root. And because square roots don't distribute nicely and break down, taking the square root of 2k plus 1 doesn't feel like something that's going to really get me to a whole bunch of integers. Almost always when we take the square root of integers, we get all sorts of irrational numbers and things that aren't integers. So it seems like a bad direction to go. So something that's nice is if we use the contrapositive, which we should think about before we start writing our proof, is that it turns the direction around, it turns our assumption around. So just being quite literal with the contrapositive, we would say if n is not odd, then n squared is not odd. And if we translate that a little bit, if you are not odd, then and you happen to also be an integer, natural number, then you must be an even natural number. So what we're going to prove instead is that if n is even, then n squared is even. Now we're ready to begin our proof of our lemma. So this is the new step that we need. Since we're going to proceed by contrapositive, we're going to state for our reader that that's the direction we're going. So all we do is we say, and we will instead prove the contrapositive. And then we're going to state what the contrapositive is. That is, we will prove that if n is even, then n squared is even. Now, it's very important that I state this contrapositive here because everything else that flows from the structure of my proof follows from this change. That is, now my assumption is not that n squared is an odd number, but my new assumption is that n is an even integer. So that's the assumption in my contrapositive. And what will we show? Well, we'll show sort of the antecedent, the consequence of this if-then statement will show that n squared is even. That is, we will find an integer k, for which we can write n squared equals 2k. Now, just like last time, I'm going to have this necessary definition step. Recall or see here that I'm kind of reserving the letter k to be this integer that I want to write n squared as 2k as. I'm going to assume that n is even, which means I can write it as 2 times something. A lot of times I would pick k to be that something, but because k is already taken, I'm going to use my assumption that n is even, and instead I'll write it as 2 times l, where l happens to be an integer. That really seems to be the only relevant definition here. Now we move on to our steps, and in this case things are actually a bit easier than they were with our standard direct proof. So first, what we're going to do is substitute in 2l for n, so that when we square and we consider n squared, we're really looking at 2l squared. Here, we don't have to FOIL at all, we just have to distribute that square to each piece that's inside the parentheses, and we end up with n squared being 4 times l squared, which we'll rewrite as 2 times the quantity 2l squared. Now remember, my goal is to take n squared and write it as 2 times something, but a little bit stronger than that. I want to write n squared as 2 times something, where the something happens to be an integer. So this last step here, I say, because l is an integer, 2l squared is also an integer. That step here is to stress that yes, I've written n squared as 2 times something, and in fact, the something, the 2l squared, happens to be an integer. Now, according to my definition for an even integer, I've done exactly what I needed to show. I've therefore shown that we can write n squared as 2 times k, where k represents this 2l squared. Just change this right here to a k, then I've written n squared as 2k, where k belongs to the integers, and this justifies that n squared is an even number, completing our proof.